All right, hi class. Welcome back to CS360V Virtualization. So today we're going to talk about the basics of virtual machines. So we're going to get started right into the first topic, virtual machines. Again, like when I usually teach this class in person, it's very interactive. Like people ask lots of questions. So I would encourage people to sort of like try and do that. So my TAs are all like on the Zoom call. So anytime you have a question, if you do like a raise hand, they will sort of like pick that up and then call me and then we can do that. Let's see, and like also use the chat to ask questions. Like periodically we can look at the chat and like I'll answer questions from there. But try and use chat for questions where like you're okay with getting answers a little bit delayed. If I'm explaining something and it doesn't make sense to you, sort of like, and you want to sort of like talk about it immediately, like do raise hand and we'll answer that right away. Okay, does it make sense? Okay, all right, cool. So let's get started. So we're going to talk about virtual machines and how we do virtualization of that. And before we sort of like jump into virtual machines, I think a good sort of like starting point is how in normal operating systems we are already virtualizing CPUs. So for example, like if you have a single CPU, right? You can actually run multiple processes on it. So let's say P1, P2, P3. They're all going to run concurrently, basically on the same CPU. They don't know about each other, and they all think that they are the only process that is currently running on the CPU, right? This has nothing to do with virtual machines. It's just like how virtualization is done in current operating systems, right? So we're just going to review that and how we're going to do this. So to sort of like remind you, in every process there is basically two modes. There is user mode, and then there is basically let's call it root or hypervisor, supervisor, or kernel. Okay, so every process can run in one of these two modes. And normally a process is running in user mode. So for example, when you are multiplying two numbers, right? Or when you are pushing something to a process's stack, all of that is like user mode instructions, right? However, occasionally you will have to do stuff that requires support from the kernel. And at this point, you do a system call. And a system call is how a user mode process becomes a kernel mode process, right? So you do a system call, and then once you do a system call, then the kernel is invoked. It does something on behalf of the user mode process, and then you sort of like return back from the system call to user mode. Okay, so this is all sort of like normal stuff that you should have learned in CS439. I know there are some students in class who have not taken CS439, so this is sort of like to refresh your memory. Okay, all right. So so this is how it typically works, but like from a hardware perspective, right? How do these things work? And the answer is basically two things. So one is in hardware there is basically a register which holds the current mode of the process. So normally, let's say it's in, let's say, user mode, and whenever whenever you do a system call, this basically is switched to kernel mode. Okay. Now, you can only run certain functions if you are in kernel mode, right? And you can only access certain data structures if you are in kernel mode. So the fact that there is in hardware a bit which tells you whether in user mode or kernel mode is sort of like part of the infrastructure required for this. So that's part of it. Another thing is, how do you actually switch from user mode to kernel mode, right? So when you do a system call, what happens is a trap is generated. Okay, so this trap is kind of like an interrupt, and what it is basically saying is that freeze everything that this process is doing. We are now going to jump into kernel mode. So we're going to access some of the the data that the user mode process has. We're going to use it to basically do a system call, and then we will return, right? When you're doing a system call, what you're really doing is you're basically generating a trap after laying out basically the data required for system call. So for example, if you're doing a system call, this could be like, syscall number, and then, arguments for the system call. So when you do a system call, you basically lay out the data for the system call in a very predefined way, where the trap understands what's going on, the system call understands what's going on, so do the kernel and the user. So everybody is on the same page regarding what is the information that is required for a system call, and when you do a system call, you lay out this information and then you generate a trap, right? Upon getting this trap, the kernel then looks at the information in the system call number and in the arguments for the system call, and then goes ahead and does the system call on behalf of the user. So that's how a trap works, and you use information that the user mode has in order to change from user mode to kernel mode and then execute the system call. Okay, does this make sense so far? Okay, so you need this infrastructure to handle user mode and kernel mode, right? If you don't, if you imagine that there is a world where we don't have the kernel and everything runs in user mode, and you don't have to switch between different processes and so on, you don't need all this infrastructure. The process would run directly on the CPU. The CPU would just execute instruction after instruction. We wouldn't have basically the bit, and we wouldn't have like traps and interrupts and so on. Okay, so this thing, another way to call it is a ring. Okay, so the ring is another sort of like fancy name for a privilege level. So when the bit is, let's say, 0, you are in user mode, and you are in basically, let's say this is ring 0, and then this is the ring 1. Okay, so when you're in user mode, you are in ring 0, and when you are in kernel mode, you drop a ring and you execute in, when you're in user mode, you're in ring 1, and when you want to execute a system call, you drop down to ring 0. Okay, so this is provided by the hardware. So the hardware itself has this notion of like different privilege levels, and some code can only be executed in a certain privilege level. So all this is provided by the hardware for us, right? So using these different rings and your traps is how we do normal process virtualization. Okay, all of this will be required for virtual machines also. So that's why I'm sort of like going through all of this. Okay, all right. So, so now that I've reviewed that, we come to how a virtual machine is going to be virtualized. Okay. And remember that in a virtual machine, you have a physical resource, and what you're going to do is you're going to virtualize it to get multiple smaller virtual resources. Okay, so virtualization is like really old. So the very first time something was attempted was back in 1974. Okay. When IBM did something called the CP67. Okay, so one thing I want you to remember is that virtualization is driven by economics, by the desire to have higher utilization of your machine. So even back in 1974, IBM was basically saying, we have this big machine, it's being highly underutilized, how can we increase utilization, right? And the sort of like idea they came up with was like, okay, what we're going to do is we're going to have one machine, and we are going to basically give virtual machines to different users. So that each user, when they log in, they get basically their own operating system, they get their own devices, they get their own memory, everything, right? So this is a step higher than just running different processes for basically two reasons. So one is, if you're running a process, if one of the processes is malicious and does something, it could bring down basically the whole kernel, including all the other processes that are running on the same machine, right? So there's no there's no strict isolation between different processes, right? If a process triggers a bug in the kernel, then it brings down all the other processes on the same machine. Okay, so in a virtual machine, you have much stronger isolation, right? So inside each virtual machine, we have, if we look at this, right? So we have an operating system, and then we have different processes on top of it. Okay, now if one of these processes is sort of like, does something wrong, it can only bring down this OS and, of course, all the other processes on the same machine, but it cannot affect the other virtual machines, right? So one of the big properties that we want in virtualization is isolation. Okay, we want the property that basically when one virtual machine or one process inside a virtual machine does something, it does not affect the other virtual machines. So it's sort of like an important property to have. Okay, another property is efficiency. Okay, so this is less of a hard requirement than isolation because the early virtual machines were actually not that efficient. But the idea was that you wanted to be somewhere close to the performance of the actual machine. Like if this machine could do some operation 1,000 times per second, you wanted the virtual machines to be able to do something close to that. You didn't want it to be like one operation per second, right? So you wanted to be in the same ballpark as the sort of like underlying hardware. So you didn't want it to become really, really slow because of that. So that's one of the goals of virtual machines, right? You want to have efficiency so that to the person who's using the virtual machine, at least most of the time, it seems as if they're running on the actual hardware. Okay. Another important property is encapsulation. Okay, so this is the idea that basically everything that is required or all the state about a virtual machine can be sort of like neatly wrapped up. Okay, and if you had a different physical machine, you could move it over to the different physical machine. Okay, so basically you could run it on a different physical machine, right? So what this means is you are able to sort of like very neatly separate out the state of the virtual machine from the state of the underlying hardware, right? So you can only move it in this fashion if you can do that, right? So if like part of the state of this machine was like, like intertwined with the state of the physical machine, then it's much harder to do that. So you want to encapsulate all the state of the virtual machine and easily move it between different physical machines. So a different way to put it is like portability. So you want to be able to run on different instances of hardware. You want to be able to move your virtual machine. Okay.
We have a question.
Yes.
So, Professor Vijay, I have 2 points. So, one about isolation. So, when earlier OSs were developed, they tried to isolate processes, OS from the processes and processes from each other. So, it's like we are pushing the problem now. It's the same problem, but at hypervisor level with other OSs, right?
Yes, that's true. So,
Okay.
Unless you're doing everything in hardware, there is always going to be a shared layer of software that you have to trust, right? Unless hardware itself gives you basically the abstraction of virtual machines.
In this case, is the shared? In this case, isn't hypervisor another operating system?
Correct. So there's two key differences, I would say. So one is generally operating systems are much bigger and more general than a hypervisor. So the number of lines of code in a hypervisor is like in the order of hundreds of thousands to like a few millions. Whereas in sort of like most modern operating systems, it's upwards of like 50 to 100 million lines of code. So you are basically reducing the amount of code that you have to trust by moving it to a hypervisor. And a hypervisor is less general than an OS, right? So if you look at like hypervisors like Hyper-V and Zen and so on, they don't have to do everything that an OS has to do. So for example, if you look at Linux, a lot of the code in Linux is actually device drivers, right? So that's where most of the code is. So whereas a hypervisor doesn't have to actually do that. So we are simplifying the boundary between sort of like your hardware and your virtual machine, and you're reducing the number of lines of code that you have to trust by going from your OS to your hypervisor.
So earlier people said that OS is going to be the hard gatekeeper, but I think we failed to keep that because they grew organically, I think, and so
Yes.
now hypervisors. Okay.
Yes, and like, I mean, in the future, I mean, I don't know if we will have time to cover this in class, but there are things like trusted execution environments where you don't trust the hypervisor as well, and then you trust the TE. So
Oh, okay.
there's lots of like different things you can do. And later in the class, actually, we will get to a security part of it where we will read very interesting papers like, hey, get off my cloud, and where you can see that the isolation property is not as well maintained as we would actually like it to be.
Mm.
Yeah. All right. Since we are pausing anyway, other questions? Okay, so I know this has been a lot of like information that I am throwing at you. Okay, so the sort of like high level takeaway I would like you to have is when we build virtual machines, we want them to be isolated from each other. We want them to be efficient. When we run something on a virtual machine, we would like it to run it at basically or near the speed at which it would run on the actual hardware, and we would like the state of the virtual machine to be encapsulated so that we can move between different physical machines. Okay, so all of these things come from basically seminal work by folks called Goldberg and Popek, who did all this in sort of like 1974. And if you go look at, there are in the class notes which are linked into the schedule, we have references for all of these things. So if you're interested, go read these papers where it's kind of like mind-boggling. Even in 1974, they were considering very much the same things we were considering today. And they came up with all these sort of like ideas of like, like how do you actually virtualize a machine? What are the requirements to efficiently virtualize a machine? Okay, so I'd sort of like recommend you check it out. All right. Meanwhile, we are going to talk about different kinds of virtualization. Okay, so there's actually like a lot, but in terms of like virtualization that's actually in use today, there's only like 3, and so we'll focus on them in class, but it's good to know sort of like all of them. Okay, so let's look at those. All right. Okay, so the very first type of virtualization is called hosted interpretation. Okay, and I think all of these things are much easier to understand with an example. So I'm actually going to erase this part of it, and we're going to work through an example. Okay, wow. All right, so let's see. So imagine that we had this sort of like hardware where we had three registers. Okay, so let's call them R1, R2, and let's say R3. Okay, so we have 3 registers. These are the physical resources that we had, and we also have, let's say, another bit, and this is basically telling you the level of privilege that you have. Okay, so the sort of like basic idea here is you have 2 registers, R1 and R2. From user mode, you can actually read and write to both of these registers. So for example, you could say something like, and I'm making this up, this is not actual compilable assembly, but like I'm making this up. So let's say move R1 1 and then move R2 3. So basically you're putting 1 here and 3 here, and let's say you're saying multiply, and then what that does is that multiplies these 2 things and then it puts the result in R3. Okay, now one in this sort of like imaginary architecture that we have, let's say that you can only clear these registers if you had privilege, right? So basically if this bit is 0, you cannot clear the registers, but if this bit is 1, then you can basically send a special clear command And what this clear command will do, it will just like erase everything that is in these registers and set them all to 0. Okay, does this make sense? So imaginary hardware that we have 3 registers, we have a bit which basically tells you what privilege level you are in, and if you're at privilege level 1, you can clear these registers. Okay.
I'm sorry.
Yeah.
If we have write access to these 3 registers, what's keeping us from just moving a 0 into all 3 of them?
Oh, the question is like, like if we can we have, do we have write access to all 3? We do not have write access to R3. So R3 can only be, and the rest I guess, but R3 can only be cleared by using the clear command. You can actually set R1 and R2 to 0 whenever you want. Does that make sense?
Yeah, thanks.
Okay, all right. So that's an important point. So,
So the
Yes.
0 bit only controls your write access on R3, right? But like on R1 and R2, you can do whatever you want.
correct. So R1, so okay, maybe a simpler way to explain this is that R1 and R2 are kind of like user mode registers. You can set and clear them whenever you want. We have the special mult instruction which will multiply R1 and R2 and put them in this kernel mode register R3 where you can read, but you cannot actually sort of like erase or do anything other than using the mult instruction and the clear instruction. Does that make sense?
That makes sense.
Okay, cool. So let's run with this. I'm making all of this up on the fly, so yeah. Did we have another question?
Yeah, sorry, I have a question.
Yeah, please speak up, it's hard to hear.
So why don't you just write 0 to R1 and use the multiply instruction to clear R3?
That's true, yes. So if you can write 0 to R1, you can actually clear using that. Okay, so let's actually modify the system a little bit, so because it turns out it was too easily virtualizable. So let's say you cannot write 0 to R1 and R2. To write 0, you have to use the clear command. Does it make sense? Okay, so I'm just going to continue. Okay, so 0 is a special value. To write 0, we need to use the clear command. Okay, all right, so we have this physical hardware, and what we really want to do is we want to take this physical hardware and we want to virtualize this so that, let's say there are 3 users. All the users see this hardware, right? So they see all of these bits, they see all of these registers. Okay, so they all think that they are the only person using this underlying hardware, but we are really supporting 3 different instances. So the first thing that should sort of like strike you is that if we wanted to do virtualization, we need more than the resources being virtualized, right? So before like the idea basically is when like let's say user 1, let's call this user 1, and then user 2, and then user 3, right? So when user 1 is running and when you want to save that state, we need somewhere for that state to go, right? Same for U2 and same for U3, right? So if we want to do virtualization, we're going to need extra memory. So let's assume that we do have, in fact, extra memory. Okay, and this memory is slower than R1, R2, and R3. So when we save state and we restore from state, we are actually accessing something that's a little bit slower than this, right? So already I think you can see the cost of virtualization sort of like coming up, right? So the registers are really fast, but in order to switch between like user 1 and user 2, we would have to save to memory and then restore from memory, right? So when we are doing that, it will be slow because we are reading memory, and the memory is, let's say, 10 times slower than your registers. So you have to wait to get all the information back, right? So does that make sense? So that's one part of it, right? The second part of it is that how do we actually sort of like virtualize instructions that access this hardware? So in hosted interpretation, what we do is we basically allow the user to execute different instructions, and what we do is we trap after each one of these things. So for example, let's say that user 1 is executing all of these things. Okay, so the user 1 tries to execute move R1 1. Okay, now if there was no virtualization, this would execute directly on the CPU. Okay, if there was no virtualization, we would execute directly on the CPU, but we cannot allow this to happen in virtualization, right? So if we allowed direct instructions to execute, then what user 1 might do is change something that user 2 was trying to do. So there wouldn't be any isolation between the different users, right? So because of this, what we do is we trap on every instruction. Okay, so basically when user 1 tries to do move R1 1, we get that instruction, we trap, and then instead of the user doing that, we, which is basically our hypervisor, we execute that instruction, right? So so what in fact ends up happening is that the instruction goes to our hypervisor. Our hypervisor then does different things and then executes it on top of the CPU. So the raw instruction is never executed directly on top of the CPU, right? So that's essentially what hosted interpretation means. We are going to take every instruction that the user tries to do. We are going to interpret that based on our host or our hypervisor, and then we are going to execute the sort of like safe version on top of the CPU. Right? So you can imagine that, for example, when the user 1 tries to execute move R1 1, then we might want to basically save whatever is currently in the R1 register, save it back to memory, and then allow user 1's instruction to execute. Right? So before user 1 can start doing something, we would want to save the current state of the registers. So what the hypervisor would basically send is basically, let's call it like a save instruction, and then once that is done, then it's going to do the R1 to 1 instruction. Okay, so at this point we are good, and basically the next instruction that the user tries will have to go through basically the same thing. It comes to the hypervisor. Now the hypervisor knows that, like, nothing else has interfered in between, so we don't have to do save, right? We can just run the instruction directly. So we do R2 3. Okay. Now at this point, the user 1 may be interrupted by a different user, in which case we need to do a save, right? So the hypervisor will basically do a save, and in memory we will have state. Right? And what's the state that we have so far? We have 1, 3, and then 0. So nothing in this bit yet. So this is U1. So this has been saved in memory, right? So after the save, now U2 can execute, and U2 may be writing different things to R1 and R2, so that shouldn't be a problem. So at some point, then we would want to restore this state from memory back to the CPU. So let's say we do a restore. And after the restore, we can now allow the mult to run directly on the hardware, because we have put 1 and 3 into the physical hardware registers. So we can allow mult to run, and then 3 would be actually coming into R3, and then we can allow the rest of user 1 program to proceed. Does the overall flow make sense? Every instruction that user 1 or basically any other user is executing, we trap, right? We trap and we interpret what it is that they're trying to do, and then we actually do it for them. So that's what hosted interpretation means, right? In hosted interpretation, the hardware that you're trying to emulate on the physical hardware can be actually wildly different, right? So for example, in this particular example, we have similar hardware for the imaginary world and sort of like the physical machine that we have, but you can imagine that, for example, you can have more registers in your hardware, in your sort of like virtual world, and you can even have instructions that physically we cannot do, right? Because as long as we understand what the instruction is supposed to do, the hypervisor can emulate it by actually doing it in software, right? So for example, we can have a new instruction in the virtual world, which is basically like, mult x, for example. This is not an instruction that the hardware understands, but as long as our hypervisor understands what mult x is, it can then do it on behalf of the user. Does it make sense? Hosted interpretation's biggest strength is that the thing that you're emulating can be very different from the physical hardware that you're running it on top of. But the sort of like the drawback of this is that it's very slow, right? Because you're going to trap on every instruction, and for any instructions that you cannot run natively on the underlying hardware, you have to emulate it with software, which is much slower. Okay? Does it make sense? So,
Question, Vijay.
yeah. Go ahead, Tony.
Hey, first, I had a question. Could you reiterate again why, when you executed the mult, you did a restore instead of another save?
Okay. So in the particular example that we are walking through, what had happened was that we were executing the program of user 1, then there was a context switch, and then so we had to save stuff, and then before we can continue execution of user 1, we had to restore from memory. So it was basically the example that we were working out.
Okay, but if the save state of the registers was already in the memory, was the only reason we restored it in that case because the mult had to operates on R3? If it was just some other move command, for example, would it just write it directly to memory, or? So
mult requires that the thing it is multiplying is already in R1 and R2. So we need to set that up again before we can run mult.
Right, okay, cool.
Yeah.
Thank you.
Yeah. Other questions? All right, cool. So do you have another question?
I have a question on the chat.
Oh, yes, this is a good chance to do that. Okay. Is the hypervisor running on a host OS? Is it in user mode or kernel mode? Okay, so in the particular example that we are working on, it is running on the hardware, it is running in kernel mode. So basically it has all the privileges of an operating system, basically. Okay. All right. In this particular example, we didn't have really another host OS, but we'll sort of like get to that. For now, you can imagine that the hypervisor is running directly on the hardware. So it's kind of like an OS, just that it does a little different things. Okay. All right. Okay. All right. Okay. So to coming back, what we looked at was hosted interpretation. The idea is that we trap on every instruction. If we can, we then natively do it in hardware. If we cannot do it natively in hardware, we emulate what the instruction was supposed to do. So this is very, very flexible. And if you think about things like, like how do you run a Game Boy console on top of your PC? They are using hosted interpretation. So every time you see things like this actually runs the Mario game inside of your browser, they are using hosted interpretation because they are taking the virtual thing, which is basically the hardware that Mario expects, and they're emulating it on top of your sort of like browser or your x86 machine. So hosted interpretation is very, very flexible, right? And it actually works very well for things like games where the speed of like the game is really limited to the speed of like human interaction, right? So you have to like jump between things and so on. And the hardware is fast enough to keep up with that. Because remember that your bare metal can run basically 1 billion instructions per second. So even if like you're 100 times slower, that's still very fast. Fast enough to run Mario inside your browser. So hosted interpretation is like, it's great for certain use cases, but if you want to run Linux on top of your machine, it's too slow for that. Okay. All right, cool. So we looked at the first approach. Now we'll go to the second approach, which is basically trap and emulate. Okay, so we have trap and emulate. Now the problem with sort of like hosted interpretation is that you are trapping on every instruction. right? And this is horribly slow because like instead of just letting the instruction run, you are trapping, considering what it's supposed to do, and then doing it. Now, if this was an instruction that could run directly on hardware and you didn't really have to do anything, for example, in our case, when you did move R1 to 1 and R2 to 3, you're not really doing anything special here, right? I mean, the hardware already knows how to do this. So the trap and emulate is taking advantage of the fact that for most instructions, you don't actually have to do anything and you can actually allow it to run on top of the CPU. All you really need to do is before you start executing the sort of like user program, you have to set up the conditions correctly. So you have to restore stuff from memory as required. But after that, you can basically let it run, right? Now, there is a catch. You cannot execute every instruction in this way. So for example, when you try to execute things like, like clear, which requires privilege, then you need a trap, okay? So another way to think about trap and emulate is a selective version of hosted interpretation where there are two things that are required. So first is we need to be able to trap on privileged instructions. Okay, so we absolutely need to be able to trap on privileged instructions. So you might imagine, okay, like what else can we do? Like you could fail silently. So imagine that user mode program is running, it tries to do clear, it doesn't have enough privilege to do clear, it just fails silently. That would be bad, right? So what we'd want is for clear to cause a trap so that the hypervisor can then notice, user 1 is trying to execute clear, let me fake execute clear for it, right? The hypervisor has all the privileges, so it can clear the registers on behalf of user 1, but it cannot allow user 1 to execute privileged instructions directly. It has to be involved, right? So this is a very big security consideration. You cannot allow any virtual machine to directly run privileged instructions, because if you did, then they would basically wipe out everything else and then take over the machine. So you cannot allow them to do that. So the restriction or the requirement is that every privileged instruction executes results in a trap. Okay. All right. So we're going to actually continue with basically the same example, but I want to show you sort of like a weakness of this trap and emulate approach. But actually, let's first run through the default stuff and we'll see how that works, right? So so let's see. Okay. So all right. So we are now using trap and emulate. We have the same program, user 1. Before user 1 can run, the hypervisor has to basically, if required, restore everything from memory so that user 1 can run. So that part is still there. So let's assume that that part is done. Now, when the user executes move R1 to 1, it goes directly to the CPU. It does not go to the hypervisor, right? So when you do move R1 to 1 and then when you do move R2 to 3, both of those things actually execute directly on the CPU and they physically change R1 and R2. This is basically similar to a process executing on your on your normal machines, right? When a process is running, it actually is changing registers on your physical machine. It is putting things into your stack, which is in memory. So it is physically doing things, right? But when your process tries to do something that it shouldn't, then a trap is sort of like triggered, right? In the same way, basically, when you have mult happening, okay, that goes to the CPU, so far no problem. But when a trap has happened, that has when you do clear, that has to result in a trap. Okay, so the hypervisor then looks at it and sees, it's trying to do clear. We don't have to do any context switch or anything, like only user process 1 has been running so far. Let's go ahead and do clear. The hypervisor will do clear on behalf of user 1. So user 1 is not executing clear. The hypervisor is executing clear on behalf of user 1. So on the physical CPU, then basically everything goes to 0. Okay. Now, while the clear thing is happening. The hypervisor will be in bit 1, right? Because when you are executing clear, you need to be in a higher privileged mode. So the hypervisor would have set bit 1 to set this bit to 1, and it would have basically then cleared all the registers. Okay, and here comes sort of like the problem. So imagine that there is a different instruction. So let's
Vijay?
Yes.
For that question.
yes, go ahead, Barrett.
Yeah, I'm just curious. So in the hosted interpretation model, we were trapping on every instruction. And I'm wondering why, if the registers are protected during a context switch where we save the register values in memory regardless, why would we trap on every instruction even if we don't require root privileges?
So we trap on every instruction because we cannot be assured that that instruction is actually something that we can execute on real hardware. So the idea with hosted interpretation is that you could execute, for example, multex, which has no parallel in real hardware. So you have to trap, you have to look at what it is trying to do, and then you can do it. And in some special cases, you actually can run it directly on the hardware. But in hosted interpretation, the sort of like default use case is executing something that is different from your host hardware.
Okay, and so we're saying hosted interpretation because we're just sending all of our instructions to the host and letting them decide what needs to be done.
Correct. Yes. So in our particular case, we are calling the host a hypervisor, but that's exactly the thing. The instructions go to the host interprets the instructions and then executes them on the physical hardware.
Okay.
Mm-hmm. Other questions? This is great, by the way. Like, I mean, I was kind of I was concerned that, like, with the Zoom medium, we wouldn't be having questions. But it's great, keep the questions coming. It's important that we understand the stuff well rather than covering material. So keep it coming.
I had a question about the rings, but maybe it can come later. So the thing is, right now we just have 2 rings. Mm-hmm. So there will be one for hypervisor and one for everything above it, which is user space. So if supposingly we have operating systems on hypervisor mm-hmm. and applications on the OS, mm-hmm. then there will be an efficiency loss for the operating system, right? Like within the operating system, if the application traps, like the OS won't be able to come in with a new level.
Yes. So let me sort of like, we haven't gotten to that part yet in class, but sort of like, let me rephrase the question. So if like, when we're doing virtualization, right, we have basically 3 distinct privilege levels. So we have the user process. So for example, in the figure that I erased, we had P1 inside virtual machine 1. Virtual machine 1 has its own OS. So P1 is in one privilege level. The virtual machine's OS is in a different privilege level. And then the actual hypervisor that is running on hardware is in yet another privilege level, right? So we have 3 privilege levels. But sometimes on hardware, you may have, for example, 2 rings, right? So we have 2 distinct privilege levels that the hardware provides. So what happens then? Like, and the answer then is, you run your virtual machine operating system at a lower privilege level. So basically, in a normal system, your OS would run in ring 0, but in a virtualized system, your OS would run in ring 1. So the OS now itself is prevented from doing certain things, like touching certain registers. So when it tries to do that, it raises a trap, and the hypervisor does it on behalf of the OS. But we'll sort of get into the details in a little bit, but this was sort of like a good question as to how the privilege levels that we have, how do they map to the physical ring structures that we have. And when we have more privilege levels than physical rings, we have to run multiple of them on the same ring, and that causes inefficiency. Okay? All right. Other...
One more question on the chat.
Okay. What mechanism is there to determine whether to run on the hardware directly or go to the hypervisor in trap and emulate? So it depends on the instructions that we have. So when you are executing an instruction, so basically if you do not have the required privilege, it will cause a trap, right? Normally, whenever you're trying to do, let's say, clear, let's say it causes a trap, and the sort of like OS will then step in and then do clear for you. Now, instead of the OS, the hypervisor is doing that for you. So it depends on the physical way in which the instructions are executed on the hardware, whether they cause a trap or not. Because unlike in hosted interpretation, we are not running everything through a host, right? We are actually running it on the physical hardware. So it's sort of like up to the physical hardware whether it causes a trap or not. Does that make sense?
But when you run the first instruction or you resume from executing your instruction, you still need a check, right? Otherwise, how can you like move your register from memory back to?
Right. So there's stuff that the hypervisor will do, which is like restoring from memory and then saving to memory and stuff. So that's separate from what the process or the user itself does, because the user never sees a save or a restore. It's all like transparent to the user, right? They don't even know that it's being saved in memory and then being restored and so on. So there is context switching between different virtual machines, and yes, that definitely requires a lot of privilege, but it's not something that the user themselves see. So that's mostly done whether, like for example, in all of not in our imaginary example, but in the physical machines that we have a timer interrupt every so often. And on the timer interrupt, that provides a chance for the current process or the virtual machine to give control back to the OS or the hypervisor, and the hypervisor can save state and restore state and so on.
Okay.
All right, cool. So, all right. So, coming back, we have trap and emulate, and we allowed all these instructions to run. When clear tried to run, a trap was generated, and then the hypervisor was able to clear the register on behalf of user 1. Okay. The hypervisor, while doing so, has set the bit to 1. Okay. Now, the problem here is, let's say that you had another instruction, right? Which is, let's say, read bit. Okay, so now the sort of like problematic thing is, if you have certain instructions where just after the instruction is sort of like done, you expect certain bits to be in a certain state. So for example, let's assume that normally after clear is done, you expect to be in a privileged state, right? So you can do more privileged instructions if required, and then you can give up your privilege. Okay, let's say that that's the case. So after clear, the expectation in a non-virtualized system is that if you read the bit, that is set to 1. Okay, so that's sort of like the expectation, right? Now, the problem is that when the hypervisor is setting this bit 1 that it has, if the bit 1 is not synchronized with the imaginary bit 1 that user 1 has, right? So in the state of user 1, there is this bit also, all right? Now, the problem arises if, like, basically, when you do this read bit here, let's say that because you did a save and a restore, let's say that's at 0. Okay, because this bit is basically reflecting whether you did a clear or not, right? So that has, so when you run this program, let's say at this point, and then you saved and then you restored and you came back, if this bit is not once again set to 1, then you have a problem. Okay, so to sort of like reiterate the problem, the bit that we have is what we call sensitive data. Okay, so just as when you try to do a privileged instruction, it causes a trap. Whenever you read sensitive data, it is supposed to cause a trap. Okay, and then the hypervisor can then fake whatever the bit is supposed to contain, right? But if the instruction set that you have, if it allows you to basically read sensitive data without causing a trap, then there may be situations where you can basically read that bit and say, hey, like I'm not in hypervisor mode, even though I expect to be, because like I'm a virtual machine. So you're able to break through that illusion, right? So on a physical machine, right after you run clear, the bit would be 1, but in a virtual machine, it may not be 1, and therefore you can identify whether you're running directly on the physical machine or you're running on a virtual machine. Okay, so because of this, whenever you're trying to read sensitive data, it must cause a trap. If it does not cause a trap, then you are able to basically tell whether you are in a virtual machine or not. Does it make sense? I know there was a lot very quickly. So to sort of like make this more concrete, right? To pop back from our imaginary world to our real world, on the x86 hardware, okay, there is a flag called the Eflags. Okay, so there's an Eflags register. Now, one bit of this Eflags register basically tells you whether you are in supervisor mode or not. Okay, now basically, even if you are inside the OS of a virtual machine, your supervisor mode bit on the hardware would always be set to 0, right? So let's actually run through this, right? So non-virtual setting. So if you are the OS, then bit is 1. So that's the expectation, right? But if you are virtualized, then the OS cannot run at the highest privilege level. So the OS will then see that the bit is actually 0. Okay, so you have this register that does not cause a trap when you read it. Okay, so basically I should highlight this. No trap. So you can read the Eflags register without a trap, but unfortunately it is sensitive. It tells you whether you are in hypervisor mode or not, or sorry, when you are supervisor mode or not. This is okay if you are running user code where you don't expect to be in supervisor mode, but if you are running OS code inside the virtual machine, you expect this bit to be set to 1. So when you see it set to 0, like now there is a problem, right? So you know that you are not running in the highest privilege level. Does it make sense? So this particular problem is why we had to wait so long for virtual machines. So this is basically why the x86 instruction set was not considered to be virtualizable, right? Because even though you could trap on many instructions, you also had things like Eflags where you could read sensitive data without causing a trap. So how do you fix it in x86 if you're trying to create virtual machines? You have to trap on everything, because otherwise it's a big security hole, right? Like you're running a virtual machine, it reads Eflags, then it sees that it's not a supervisor anymore, big problem. So because of this, x86 was not considered a virtualizable architecture. And sort of like the surprise is that if you went back to 1974 and if you read like the sort of like pioneers then like Goldberg and Popek, this was one of the conditions that they put forth for whether you can virtualize something efficiently or not. And the condition was that if you access any sensitive data, it must cause a trap. If you try to execute any previous instruction, it must cause a trap. So x86 violates one of these things. You're accessing sensitive data, it is not causing a trap. And therefore it is not an efficiently virtualizable architecture, right? So until basically 1998, this was the state of the art where you could not virtualize x86 efficiently, right? Because for security, basically if you are if you're running virtual machines and you're giving it to users, you can't tell them, hey, don't look at the Eflags register, right? It has to support the full x86 architecture. So then you'd have to trap on every instruction. You're back basically in hosted interpretation land, very, very slow. Okay, so that was the state of the art when you had only trap and emulate. Questions so far?
why you cannot only chap on these instructions that read
Sorry,
sensitive data?
can you speak up?
Oh, sure. Why you cannot only chap on those instructions that read sensitive data?
Because
Like-
we don't have access on the hardware, or like we can't change the hardware as we want. So x86 is already there, deployed on millions of machines, and it does not trap on sensitive data. So as the designer of a virtual machine, the hardware is fixed for you. So you are operating on top of the hardware. So this is a limitation that you have to play with. So you cannot change the hardware based on your requirements.
Okay, I see.
Other
Yeah.
questions
We have another question in the
chat?
Actually, 2 questions.
Okay, we have lots of questions. Okay, all right. So, which architectures is the most virtualization friendly in the sense there are few or no instructions that access sensitive data without a trap? So, this is jumping ahead a little bit in our history of virtualization, but basically the answer is today everything, because we have hardware support for virtualization. So the Intel and AMD, they realized that this was pretty bad what they were doing, so they built virtualization support right into the architecture. So basically, when you access Eflags, for example, a trap is generated. So they closed that loophole. So because of this, both AMD and Intel, all of their architectures are eminently virtualizable today. Right? Okay, why is it bad if a program knows it is not in supervisor code? Good. So imagine that you're writing an operating system, right? And sort of like best practices is that you write basically assert statements for things that you know must hold, right? So if you're accessing, let's say you're in the middle of a binary search tree, the root must not be null. So let's say you put an assert statement in there, right? And every function will hit this assert statement and it will not be true, and I mean it will be true and it will go on. Similarly, for accessing kernel data structures, one of the sort of like important conditions that must hold is that you are in supervisor mode. So you can imagine that across the kernel, this is an assumption that they have, which is encoded into assert statements and so on. So if you now have this assumption that you're not in the supervisor mode, then you'd have to rewrite the operating system. And this is again jumping ahead, but you have something called para-virtualization, where an OS knows that it is not running on the hardware anymore. So it knows that there is a hypervisor beneath it, and it makes different assumptions about the code, and it is able to work with the hypervisor to get what it requires. So it basically knows that like it's operating at ring 1 rather than at ring 0. So it does not care. Like whenever it wants something done, it just tells the hypervisor. So you could totally do that, but it requires rewriting the operating system. So para-virtualization is sort of built on this idea, but it requires rewriting the software, the operating system, so that at all the places where you assumed you were, like in ring 0, now you basically make a call to the hypervisor to say, hey, can you do this for me? So it's not a trivial effort. You have to change lots of different things in order to do that, but it can be done. And that's basically the idea behind para-virtualization. Okay. All right, so we had all those excellent questions. So anyway, so we would have to wrap up in another 10 minutes or like 5 minutes. But let me actually like run through all the different kinds of virtualization there is, and we sort of like go over them in detail in the next class. Okay, and I've already mentioned a little of them today, but we'll sort of like go through the rest of them. Okay. Okay, so the other idea is binary translation. Okay, so trap and emulate is a very reactive idea, right? So you're like, let's execute this instruction. If it's safe, let it execute. If it's not safe, we're going to handle it so that it's safe, right? So that's basically the idea behind trap and emulate. And it's a very reactive instruction, because unless you execute that instruction, you don't know ahead of time what you're going to do. So you're just going to play it along until you get to a problematic instruction, right? In binary translation, you have a more proactive approach. So basically what you're going to do is you're going to take an instruction, a program that looks like this, where it has like, like all direct hardware instructions, move R1, move R2 and everything. You're going to translate this program so that instead of doing any, potentially problematic stuff like read bit and clear, you replace them with other instructions that are safe to execute, right? So for example, what would you do, right? So instead of like clear, which is a privileged instruction, what you're going to do is you're going to say, in the memory that is meant for U1, go and clear field R3, which is totally something that you can do in user space, right? So you're not actually changing the hardware register, you're changing the state of the virtual machine, which you can do from without privilege, right? Similarly, whenever you have a read bit, and that read bit was supposed to read the hardware bit, you change it so that you read basically U1's virtualization state dot bit. And we can ensure that the memory state that is meant for user 1 can be kept in a synchronized manner. So we basically run through the program and we basically replace all of the privileged instructions or instructions that access sensitive data with safe instructions that operate on top of the state of the virtual machine instead of directly on the hardware. Okay, and we'll go over this in a little bit more detail in the next class, but what you're doing is basically you're doing a compilation phase, right? You're taking in a program and you're translating it so that you get something safe, and then the safe thing you run on top of the hardware. So that's the idea behind binary translation. And this was sort of the chief idea based on which VMware was founded in the early 2000s. Because this could work with x86, right? You know ahead of time which are the instructions that are problematic. So when you're doing the binary translation, you can basically do, they're reading Eflags, get rid of that and do this other thing instead. Because you have this sort of like global view and you're doing all of this before the program ever executes, right? So binary translation was this like big idea which resulted in VMware being founded and the first sort of like really fast virtual machine being founded around this time. Okay, so this is sort of like big idea we'll return to. And then we have hardware supported virtualization. Okay, so the thing with binary translation is that you now have to pass all your instructions through this translator, right? Without translation, you cannot run anything on the hardware, and that has its own drawbacks, right? So you can imagine, I mean, the way I explained it, you would imagine that we take a program, we translate it, and then we run it on the hardware. This is feasible for small user programs, but really, like when you're, building these virtual machines, the thing that is most problematic is the OS, right? You want to translate the operating system inside the virtual machine. That's where all the problems are. And if you take Windows, for example, that's like 50 to 100 million lines of code, right? You can't translate all of it at once. So instead, what they do is they do it at runtime. So before you execute the program, they'll take like a big bunch of the code, translate it, then execute it on top of the hardware. Then once that's done, they'll take the next bunch, they'll translate it, run it on top of the hardware and so on. So it's sort of like a runtime thing, which has its own overhead. And this is around the time where Intel and AMD, they basically realized that, hey, virtualization is like a big market. And if we built virtualization support into our chips, they would sell better. And so we had hardware support virtualization, where the hardware basically gives you copies of the hardware state for each virtual machine. So you can basically say to the hardware, restore all the state for virtual machine 1. It has a nice memory area where it's storing all the different registers for virtual machine 1. It will save all of that to that area and then restore back. So all of the things that we were doing here, where you're writing it to memory and then restoring it back, the hardware can do automatically for you. So that's one thing hardware virtualization provides us. The other thing is, because this is done by the hardware manufacturers, they can fix things like like annoying things where sensitive data, for example, is read without a trap. So they can now say whenever you're reading sensitive data, trap, right? So that was the other support that hardware vendors provided us. But basically, once hardware supported virtualization came out, which is in like around 2005, 2009 and so on, that changed the game a lot because you no longer needed binary translation, right? You could directly run your OS on top of hardware supported virtualization, and you now had Goldberg and POPX conditions being met. Every time there was a privileged instruction, it would trap. Every time you're reading sensitive data, it would trap. So it was really easy to build a hypervisor that was efficient, that could then virtualize the above virtual machine. So this is still being used today, right? If you go look at Amazon sort of like virtual machines and Microsoft virtual machines, they're all supported by hardware supported virtualization. So this is sort of like the main technique that's used today.
But can I have a question, Professor?
Yeah.
So from the processor perspective, how do you know like an instruction is coming from the virtual machine or from the hypervisor? Like how do you know whether you should trap this sensitive data read or not?
You have different privilege levels. To sort of like repeat the question, it was kind of like faint, but how do you know when to trap and when not to trap in executing an instruction? And the answer is the hypervisor runs at a higher privilege level than the virtual machines. So the same instruction, if a hypervisor was to execute, no trap, but if the virtual machine was, the operating system inside the virtual machine, if it was trying to execute that, it would raise a trap.
Okay, I see. And another question is that with this hardware supported virtualization, does that mean we have an upper limit of how many virtual machines we can run on?
No, so it's more of a performance aspect. So if you run a certain number of virtual machines, the hardware can do something for you, it would be pretty fast. If you want to run more than that, then you do have to go out and access memory, and then it will be a little bit slower, but the hardware can still do that for you. So it's just a question of performance, and it doesn't limit the number of virtual machines being run.
Sure.
Okay, other questions?
We have 2 questions on the chat.
Okay, all right. Let's see. So how does binary translation work with self-modifying code? That's a very good question. And next class, we're going to actually get into the details of binary translation, or maybe the class after that, and I'll handle that at that point, right? Is this similar to Rosetta? I'm not really familiar with the details of Rosetta, so can't comment. But if you stick around after class, we can talk about it. Somebody else answered yes, so maybe it is. I'm not sure. Okay, so let's see. So one final thing, right? So we also have para virtualization. So this was an idea that came before hardware supported virtualization, okay? And the idea is basically what someone in class had, right? The idea that, why do we want to keep up with this illusion that the OS is running on top of the hardware? What if, we didn't have to provide that illusion? And the answer is that if you can rewrite the OS to work with the hypervisor instead of directly with the hardware, it turns out that you can have big performance gains versus, trap and emulate or binary translation. Because you can now directly say, instead of asking hardware to do something, we're going to ask the hypervisor to do it, and it turns out that's very efficient. So para virtualization was a big idea that came, and it was sort of very popular in between binary translation and hardware supported virtualization. But and there was a time when Amazon, for example, supported both Xen para virtualization and hardware supported virtualization. But over time, the shift has been more towards hardware supported virtualization. And the reason this is so is because you need to modify the OS to work with para virtualization. So every new OS version that comes out, it has to work with para virtualization. Whereas with hardware supported virtualization, you don't have to do any hard OS changes. So this is strictly easier to sort of work with than para virtualization. So that's sort of what happened. And I think we'll probably stop here in terms of new content. I'm still here if people want to ask questions, but we will sort of resume with new content on Thursday. All right. So other questions? For the person who asked the question about Rosetta, can you sort of talk about it? James or Bennett?
Yeah, it was the Mac tool that allowed PowerPC to emulate x86.
I see.
And now
okay.
it's 86 to ARM.
Got it. Okay, makes sense. Yes. Could you go over para virtualization again? Yes. So normally when we write operating systems, it directly interacts with the hardware. So it does things like change this register or read this register and so on. And to do many of these things, it requires privilege, right? And you need to be in the most privileged mode in order to do this. In para-virtualization, when the OS wants to do similar things, it realizes that it's not running at the highest level of privilege. So what it does instead is, instead of like changing the register directly in hardware, it asks the hypervisor. So it is aware that there is a hypervisor. So it does what we call a hypercall. So it does a hypercall to the hypervisor and says, hey, can you change register X for me? And then the hypervisor does that. So instead of like directly running on the hardware and changing registers, it interacts with the hypervisor, and the hypervisor does the actual privilege stuff. So imagine how for a normal process, it does system calls to the operating system to do privilege stuff. In the same way, the OS now does hypercalls to do privilege stuff using the hypervisor.
What performance benefit is there to making hypercalls versus trapping?
Traps are very expensive, basically because you cannot, you continuously have to provide the illusion that you are the only one running on hardware, and for example, in this imaginary architecture that we had the bit that was being that was sensitive, you had to monitor it at all times, right? Whereas in para-virtualization, the user knows that they're not running on the actual hardware, and they would not use the bits, the information in bit to actually run anything. So imagine all the times we had to trap because we were reading bit in our imaginary hardware. Now we don't have to do that. So that's the difference between para-virtualization and trap and emulate.
Okay.
Okay. How is trapping set up for privileged instructions? Aren't traps normally triggered via special instruction? So there's two aspects to that. So you can actually call a trap, like for example, how system calls are done. You can also have things where whenever you execute an instruction, the hardware will then look at the privilege bit, right? So for example, the bit that we had in an imaginary architecture. So if you execute an instruction and the bit is 0 and the hardware expects it to be 1, that will cause a trap. So you can trigger a trap, and the trap can also be sort of like triggered based on what the hardware finds when it's executing an instruction. So for example, if you are trying to divide two numbers and one of them is 0, that causes a trap automatically. Okay. Are there any potential advantages of running partial para-virtualization even on hardware-supported virtual machines, like I/O, for example? It's an interesting question. So there are certain use cases where Amazon, for example, even today they are running para-virtualization. And sort of like another way to think about it is that like things like GPUs and FPGAs and stuff, virtualizing them properly requires like hardware support, but hardware support is not always sort of like there, right? I mean, our current hardware and the heterogeneous stuff that we execute is ahead of like the hardware support that is provided, right? So in these cases, para-virtualization actually helps a lot, because para-virtualization is basically getting the same hardware support but in software, right? So for some use cases, para-virtualization actually is better than hardware supported virtualization. But if the only thing you're doing is running like traditional x86 instructions and accessing disk and stuff like that, then para-virtualization does not really help that much. But depending upon the specific devices that you work with, it might help a lot. Other questions?
Professor, I had a question.
Yeah, go ahead.
You mentioned that for hardware support virtualization, one of the benefits was that there was hardware support for asking, for example, what is VM1's state of registers and such. Is that correct?
Yes.
But
so, yeah.
Isn't that already handled by the host OS's context switching in that case? Because it sounds very similar to what you just described.
Yeah, it's basically the same idea, right? So when if you imagine a normal OS and you have registers, and when you do a context switch, right? Basically, on a context switch, you are saving all these registers to like your stack, for example. And there are hardware routines that understand how to do this. And you're basically doing the same thing in the case of virtual machines, where your state is now bigger. The state of a process is much smaller than the state of a virtual machine. But now hardware understands all the different pieces that make up the state of a virtual machine and can then save and restore them using a hardware command.
What other states are there involved in the are there involved besides for the memory and the registers in that case?
So there are things, for example, the sort of like privilege level registers. For example, there are registers in your hardware CPU that only the OS is supposed to be able to read and write. So all of this is part of the VM state. It's not part of a process state because the process never needs to actually sort of like read these things. So it's part of the VM state, and whenever you sort of like want to save and restore a VM, you need to save and restore all those registers. There's also things like your the device level information that you have. Like for example, if you have networking in your virtual machine, you will have virtual network queues. And the state in those virtual network queues is also part of it. So you have pointers to these virtual network queues and so on. So all of the different hardware in a virtual machine is all encapsulated together, and you can save and restore them.
Okay, cool. Thank you.
Mm-hmm. Okay. Right. Other questions? Okay. So project one, the first part of project one at least, should be released fairly soon. Sort of like keep an eye out for that. And otherwise, I will see you guys on Thursday. Right? Thanks.